Well, Kit, I'm very pleased you could join us today and to talk about your illustrious career at AECL.
Illustrious. Well, we can debate that.
First of all, how did you arrive at AECL at the Chalk River project?
It happened that when I was doing my PhD, there was a Canadian doing his PhD at the same department in Newcastle upon Tyne, and we talked to each other because he was working on hydrogen and zirconium. Strange. So I was working on hydrogen and zirconium, so we got together on this. And he was telling me that there's a place in Canada called the Chalk River Laboratories, and a lot of the references that I was coming across were from this same place. So at the time, I got to know Gareth Perry, I got to know Windsor Evans, and people like Robertson and Perriman through these AECL reports, which I used to go to the library and pick up, and I used them. So I sort of half knew the people in Chalk River, and so I finished my degree and asked them if, sent them a letter saying, hey, would you like to hire me? Little did I know that my progress reports for my PhD, there was a contract with Harwell, and Harwell had an exchange with Chalk River, and they used to see all my progress reports. So they sent me a letter and say, when can you start? So I thought that was nice. And so they sent me a nice letter saying, oh, we'll pay you, a king's ransom to cross the Atlantic and bring your family, and we'll get a house for you, and you'll have a 6-month sort of probationary period. And so that was it. So I bundled the kids and my wife onto a boat, and we came across the Atlantic, and that was an interesting exercise in itself. And on the same boat was Mike Carver. And I didn't know that, except that he's a big burly man, and when he's walking through the restaurant in the boat, then you knew who he was. And so when we came here and he was at Chalk River, that was an interesting introduction to Chalk River as well.
So there was no interview or anything; they just took you on your work, essentially.
Yeah.
Okay.
Mm-hmm.
Oh.
Well, no, maybe my colleague Bill Erickson had some nice things about it, because he actually then came to Chalk River and had a job, and he was working here. And so I don't know whether when my letter came in, they the powers that be sort of got Erickson in and said, hey, is this guy any good? I don't know.
Mm-hmm. Okay.
So yes, so it was from that point of view sort of very, very easy.
Yeah. So what year was that then?
1965.
1965.
It says so on here. I've got a resume here, so just to make sure I do it in the right order. So yes, that was 1965.
Okay. So what were your first impressions of both living here, but also of the labs at that time?
Well, we'd seen the pictures on the blurbs that the Chalk River had sent to us, and so we knew it was a pretty rural area, which was wonderful for us because we lived in a rural area in Britain. And we arrived in the middle of October, and it was warm and sunny, and we took the kids down to the beach. Mm-hmm. The water was warm, so they paddled around in there. There wasn't a soul in sight. It was a blue day. It was absolutely gorgeous. We're going to stay here, aren't we? So anyway, that was my introduction to Deep River. And I went into the plant on the Monday and went through all the bureaucracy, which was bewildering because I'd never done anything like this, because they were asking me questions on insurance and income tax and health things, and I really had no idea what this was all about. So they hand you a whole bunch of papers to studies and so on. So that was my introduction, and then you get to meet the people you're going to work with, and So what they asked me to do was to work on tertiary creep of zirconium.
What's tertiary creep?
What is tertiary creep? Well, when you do creep, you put a weight onto something, or you pressurize a tube, and the first thing it does is try to strain. Mm-hmm. And the first part of the strain, the primary part, is a little bit of creep, and after that it tends to sort of creep at a constant rate with time. So you get a certain amount of strain per hour, and that's what you measure, the amount of strain per hour. And if it gets out of hand, then it accelerates and it takes off, and it'll fracture. And clearly you don't want your tubes to start to expand rapidly and go to fracture. So that's what tertiary creep was about.
Okay.
So how do you set about doing that? And so it took me a long time to sort of understand what was involved, because the usual way to do these things is with tensile specimens. So these are just little rods of material, and you hang a weight on the end and you watch how they deform. And so you've got no irradiation. You're doing these at sort of nominal temperatures in a laboratory, and it doesn't sort of tell you a whole heck of a lot. So I had to sort of dream up some different ways of dealing with this. And so that's what I did. Not many people in the world actually are interested in tertiary creep. And the other thing that involves is you may start to get porosity in the material. And if that happens, then that reduces the cross-section again. So that means the stress is going up because the load's there. So you've got two ways of increasing the stress, i.e. because the specimen is getting thinner, and it's also getting thinner because you're forming little holes in the middle of it. So that's what that was all about. And so what you really need to do is to do these kind of experiments in the reactor. Mm-hmm. And so if they're worried about going up to a few percent strain, so doing this uniaxially in the reactors at the time was very difficult to get large strains in the reactor. So there was a man called Bill Fiddlerus.
Oh yes. Okay.
And so I worked with him. He was he tried to be as helpful as he could, without telling me what to do, if you see what I'm saying. And so I struggled for a while to do this. I wrote a sort of a guess report on just growing a cylinder under load over time, and try to put some information from the literature in terms of the effect of temperature and stress, and that seemed to sort of tell the story that it's very difficult to actually do it at an experiment on deliberately just to tertiary creep, because you've got to go through primary creep, you've got to go through secondary creep, right, before you get there. So I did that, and I did some experiments, and I sort of made a guess of how a cylinder would change with time, how its shape would change with time. And so I developed a little back of the envelope kind of model, and sort of divided it like a finite element analysis, and sort of put some creep equations in there, and watch the thing grow and watch it change in diameter. Mm-hmm. and came to the conclusion that tertiary creep was mostly controlled with the geometry of the specimen on how it deformed. So a tube, because that's what you're really interested in if you're going to deal with pressure tubes, mm-hmm, a tube would behave in exactly the same way. And so doing an in-reactor creep test is actually quite difficult. At the time, Bill Fiddlerus had pioneered a way of doing this, so making these uniaxial specimens and doing these inside a reactor. So you've got a little hole like this, and you've got to put a stress on it.
Yeah.
You've got to be able to measure the change in length. You've got to be able to measure the temperature. You've got to be able to heat it up and control it. All those things are in a hole about this big. So he'd done pretty well on that. And so there's some fine literature on that in some ACL reports and papers on that. And so I tried to do that as well, and we had to change how you measure the elongation. So that was a pretty tricky thing to do. At the time, they were using essentially changes in pressure on essentially a pressure gauge. So firing firing gas against a plate, and you get the feedback pressure. And the further the plate is away from the little hole that you're firing the gas through, then that gives you a feel for how far you've moved it. And so if you put a spike in the hole, you can get a much longer range of movement on it. And the other method I wanted to try was to use an LVDT, a linear variable differential transformer. So my first experiment was to take one of these things and put it in the reactor and see whether it would work. So we made a little device where we could move it with a clockwork and just move it up and down. You move the thing in the middle, which I've lost for the moment. Anyway, to drive it, so you knew how far you'd driven it using a little motor, and it seemed to work. It did work, but I guess Chalk River was tied up with these air gauges, and that's what we used.
What was the importance of having it in the reactor, though? This experiment, why would you have to keep it under reactor conditions for?
You want to do it in the experiment because you ask the question, when you put a pressure tube in there, is the behavior in the reactor, is it the same as out the reactor? And so what you want to do is to find out whether it makes any difference putting it in the reactor. And you could imagine that the reactor, having neutrons bombard the material, it could make a difference to how the dislocations move, how any embrittlement that might take place. So all of those were being considered. So we knew that by, at the time, people had irradiated materials, taken tensile specimens out and pulled them apart, and you find, it reduces the ductility, it strengthens it. And so there was some information on how much the material was strengthened as a function of fluence of neutrons, how it was changed by the temperature of the irradiations. And so there was a whole bunch of experiments had been done along those lines. So people like Chuck Ells had done these, and Tony Sawatsky and these people. The interesting thing about Tony Sawatsky is that he moved to Whiteshell, and I inherited his desk at Chalk River.
Oh, okay. Yes, I knew Tony a little bit when I was at Whiteshell.
Yeah. Mm-hmm. Yeah. Oh. He was a very good man.
Yes. What was he, a ham radio operator?
He was a glider.
Oh, glider. Oh, okay. Very good. Yeah.
Yeah.
I haven't heard that name for many years.
Yeah.
Yes. Okay.
So with the recent shenanigans in Europe at the moment, then his name comes up in our household at the moment.
Where was he from originally?
Yeah, Ukraine.
Oh, was he? I did not know that. Okay. Okay.
I don't know whether he actually came from Ukraine, but Sawatsky's a Ukrainian name.
Ah, okay. Very good.
I have a Ukrainian son-in-law. So, yeah, we know the problem. What we're talking about, creep.
Creep in reactor.
Creep in reactor. So, so there's two things that can happen. The material can become harder, and the dislocations can move more easily. So you get vacancies forming, and they help the dislocations climb and move, and so on. And so you can get an increase in the creep rate because of irradiation.
Right. Okay.
So the radiation is on the one hand, it's trying to slow the process down by hardening it. On the other hand, it's trying to speed things up by helping the dislocations move by creating a lot of vacancies.
And so this was important to have it in reactor for a continuous experiment rather than just samples put in and tested.
That's right. Yeah. So you do the experiment in the reactor because that's where it's going to be that's where a tube's going to be for the rest of its life.
Yes.
Now the neat thing that was happening at the time was that people like Phil Ross were doing experiments on the tubes themselves, where they made a great big sort of like I saw.
I have a fuel bundle here.
A fuel, yes. There's something about the same size as a fuel bundle.
Yes.
And what they did is they put little LVDT things which sort of poked out of the cylinder, and they drove these down the pressure tubes. So they put these through the pressure tubes and measured the shape of the
Yes.
pressure tube.
Yes.
And so when you know what it looks like at the beginning, and then you can work out the creep strain by measuring the diameter today, and then measuring it in 3 months' time, and measuring it in 5 years' time, and so on. And that's what they did. So you get this beautiful strain graph as you go down the fuel channel, because it's starting at a low temperature and going to a high temperature, and there's a big flux in the middle. So the whole thing does that, and you can see this from the expansions that are measured. Okay. So these experiments are, and this is a standard thing that they do in places like any of the reactors, the big reactors.
Yes.
They go and they gauge them, and they find out how they're doing. And this is a standard thing that they do.
They even find a little bit of extra expansion between fuel bundles, don't they? Because there's
That's
higher
right.
flux there or something?
Yeah, when you do it, you get this sort of little wiggle as you go
Yes,
across it.
yes.
So if you get these beautiful curves like that, and they have little wiggles on them as you go along. So when you do this in Russia, in RBMK, you get a wiggle right in the center, because they have essentially two fuel bundles. And so where the fuel bundles meet, you get a big change there. But they have another source of change because they have graphite bricks.
Yes.
And when you send the thing through the graphite bricks, then there's a flux depression there as well. So along a Russian tube, it goes wiggle, 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 wiggle all the way across. So it goes all like that with a bunch of little wiggles imposed on it.
Okay. And of course, their tubes are vertical in the RBMK reactors.
Right.
So that would that change things?
Not very
Probably
much.
not, no. Okay.
Well, the important things you're looking for is the flux profile and the temperature profile, and the pressure profile as well, because the pressure will change as you go down the tube.
Certainly.
Yeah.
It drops.
So you've got three things going down the tube, along the tube.
I was thinking in terms of course, sag of a channel, but that's
right.
quite different. That wouldn't have an influence on your creep then at all.
Yeah, it's all mixed together. You know, the guys that analyze these things in detail, then they have to take into account the sag, because it'll sag. You get more deformation. Yeah, the amount of deformation is very, very peculiar, isn't it? It's going down like that, and so the top is doing the same kind of thing. But what's happening to the edges, and it's complicated.
Do you think it's just a tube, and yet it's got all these
it's a
features
tube.
to it? Yes,
that's right. And so, yeah.
And of course, your concern was tertiary creep leading towards rupture,
That's
or
right,
the potential for rupture.
That's right.
Which then brings me to the question about Pickering in 1983 in August, where we actually had a huge long crack in one of the tubes.
No, that wasn't anything to do with directly with creep, What that was to do with was, in fact, you mentioned sag just now, and that was to do with sag. And it was to do with the pressure tube sagging into contact with the calandria tube.
Yes.
And when it does that, you get this enormous temperature gradient at the point of contact.
Mm-hmm.
And that has some nasty things going on for it. So what happened in G16, it was P2 G16,
right.
The pressure tube sagged into contact with the calandria tube in 4 or 5 locations. They're fairly close together. Mm-hmm. So what happened was that the hydrogen will move under a stress gradient, it'll move under a temperature gradient, it'll move under a concentration gradient. It's very mobile stuff. And so what it does at the temperature gradient, it moved down the temperature gradient and concentrated and formed hydrides. And then we got blisters of hydrides. You get a lot of hydrogen forming at these points of contact. And so in G16, there was about 4 or 5 of these points of contact. And as you know, hydrides are brittle things. Mm-hmm. And so you get a bunch of cracks forming, and these cracks linked up, and they were sufficient to exceed what's called the critical crack length. And so if you exceed the critical crack length, the crack will grow unimpeded, and that's the end of your tube, because it's grown a long way down the tube.
Mm-hmm. Mm-hmm. So this then leads me to sort of talking about hydrogen ingress in the tubes and things like this. Then you did a lot of work in delayed hydride cracking.
That's right.
So how is that different from these hydride blisters?
It's different, but it's not different. The hydride blisters are purely a temperature gradient phenomenon. Mm-hmm. Okay. But once it starts to crack, this blister will link up with this blister by delayed hydride cracking. And so that's how they linked up, and they'd form a great sheet of a crack, and that would just zip down the tube. Now, delayed hydride cracking is the other gradient that's going to drive the hydrogen. It goes up a stress gradient. So you can see if you have a high stress, the hydrogen will move to that point of high stress. So if you have a crack, then the hydrogen will move to the end of the crack. Mm-hmm. So in a end fitting, you have sometimes where there's a rolled joint, you have a large stress there, or you can do, and so the hydrogen will move to the point of high stress. Oh. So the whole way that delayed hydride cracking works is that the hydrogen collects in these places of high stress, and if there's enough hydrogen for moves, then you get a hydride forming, and if the stress is large enough, the hydride will break, and if it breaks, then the crack will extend. And so then you're on your merry way, because the crack's extended. You've got a place here where you've got high stresses, and the whole process will continue. You'll collect more hydrogen at the end of that crack, and then it'll just go in little steps. So if you look at a fracture surface that's grown by this, you'll see these little steps. You get little terraces or striations on the fracture surface, and you can see where it's been going along.
Oh, I see. Okay.
So the other thing that you can see when this happened in the Pickering reactors in 1976, was it? Yes.
83 when the big crack. Yes.
Yeah, but that was from the blisters.
Yes.
In 73 or so, there was some cracks that cracked because of the high stresses at the roll joints.
Oh, I didn't know that. Okay.
Okay. Well, should I start at the beginning on that one?
Sure.
Because that was most unfortunate, because Pickering was going gangbusters. and they'd used zirconium 2.5 niobium for the first time in Pickering 3. And the roll joints were put in very well. The people who were doing it thought they'd do a really good slap-up job, and they pushed the rollers in to drive the to make the seal, the roll joint seal between the pressure tube and the end fitting.
Yes.
And if you not supporting the pressure tube with the end fitting, then out here where there's no support, you build up very large stresses, and so this was not known until the tubes cracked. And why did they crack? Well, it was unexpected because we didn't know there was these high residual stresses. So when the original tubes were made, I guess nobody thought to even measure any stresses in there. But when they cracked, then there has to be a stress there to make the crack grow. So that's what people did. That they said, let's not have any high stresses in there. So what we're going to do about it? Well, one thing you can do is you can put a little heater in there and stress relieve it by heating it all up. So that was done in 1973. And the other thing that was done is to learn how to measure the crack. Sorry, to measure the stresses in these locations, and some of these stresses were just enormous. So that they, 500 megapascals, and very large stresses, and so that the cracks grew through the wall, and they leaked. So you don't really want your tubes to leak. No. And so this happened about 76 times in Pickering 3 and Pickering 4. A lot of times it was a big issue. And so so we measured, I'm saying we, not me, I mean the community, there were lots of meetings about these kinds of things. So what was the process? The process we decided was delayed hydride cracking. We'd known about delayed hydride cracking as a sort of a laboratory curiosity. So what you do is you take one of your tensile specimens, you put a notch in it, you hang a weight on it, and wait, and it goes crack, 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 and you take it out and you have a look at it, and there are the hydrides at the end of the notch, and you say, well, isn't that nice? Well, actually, it's not nice; it's nasty. But what had happened in the meantime is some zirconium 2.5 niobium fuel cladding had been made, and as you know, at the end of the fuel bundle, you weld on the end an end plug, and if you're not very careful with how you do that, then you can produce very large residual stresses from the welding process.
Right. Right.
We're really good at putting big stresses in things by and making big stress gradients. So this was the other way of doing it with welding. So you've got to be very careful with welding, and so some of these tubes were put in, on a shelf for storage before the people used them, and they came to use them, and they're sort of fallen apart. The ends had fallen off, or there were big cracks in them.
This in the fuel bundles?
Yeah.
Oh, okay.
And so for that, they weren't put in the reactors. They'd just been in storage, so it was just as well they hadn't been put in the reactors. Except if they had been put in the reactors, they might have been stress relieved while they were in there. So, see, this is complicated, isn't it? I do apologise. Anyway, so that was a lesson learned. So what did you do? Well, you stress relieve them, and you're very careful how you make the weld. And so when the cracks started to form in the pressure tubes in 76 or 75 or whatever it was, we had a good inkling about what it might be. So one of the tubes was taken out, and the cracks were examined, and people looked at these things, and there were several cracks in the pressure tube. There was a main crack that had gone through the wall, but there were several cracks that hadn't gone through the wall. You do a little bit of metallography on them, and you see that these nice hydrides, actually nasty hydrides, at the end of the crack. And so people say, "Ha, we've seen those in the weld. We've seen these here. We've got a problem with delayed hydride cracking." And the neat thing about these things was you could see the reactor history on the fracture surface. So what happened was the crack would start on the inside surface, and they'd grow a little bit, and then the reactor would go to power. And when it went to power, the fracture surface would oxidize. And then when it came back from being at power, it would continue to crack when it was at room temperature or at low temperature. And then it went back to power, and so on. And so you get this nice rim of fracture, and it's all pretty colors because of the oxides at different colors, at different thicknesses, and all the way through to the outside surface where it leaked.
Oh, okay, yeah. I did not know that they had leaking problems with Pickering.
Mm-hmm. Yeah. Well, so the importance of that is that you say to yourself, well, there's people who grow pipes and things, and how do they protect themselves? Well, they have a process called leak before break. Mm-hmm. And so this is a classic, beautiful example of leak before break. Now, in the way some of the institutional people who deal with cracks, they don't allow you to have leak before break if your component can have a time-dependent cracking process. So, strictly speaking, we shouldn't be allowed to use leak before break, except that we know how to control it. And so that was how we exploited this.
So how did you cure this leak before break? How did you cure this leaking business in Pickering?
Oh, well, the way it was done was to say, well, okay, the root cause of this is that you've got a great big stress there. Mm-hmm. So the guys that did the rolling did such a good job, they put enormous stresses in there. Yes. And that was the issue. So if you make these things without putting these big stresses in, then you've got nothing to crack the hydrides.
So they were over-rolling them.
They were over-rolling them.
Okay.
That's exactly the term that was used.
Yes, I'd heard that. Yeah, okay. Okay, I didn't. Mm-hmm. Oh. So now previous reactors also used a different alloy called zircaloy 2. And now you were using zircaloy 2.5% niobium, right?
Mm. Yeah.
What was the difference there? Why did they make that change?
Well, it's a stronger material, mm-hmm. and so the thought was that we can make thinner tubes because it's a stronger material, so you get better neutron economy.
Ah, okay. So
that was the driving force for that. Mm-hmm. But because it was stronger, it meant it had larger residual stresses. So that, as far as I know, there's never been a problem with rolled joints in zircaloy. And there's lots and lots of pressure tube reactors around the world using zircaloy. So there's SGHWR, there's the N reactor. I think there's a reactor in France called E4.
There was, yes.
Yeah. And so, however they joined the tubes to the end of the reactor, as far as I know, we were the only ones that had problems with zirconium 2.5 niobium. The Russians had problems with zirconium 2.5 niobium, but for a different cause. So their cause was because of the way they fabricated the tubes, and they put a lot of residual stresses within the tubes themselves, and the tubes were cracking.
Oh, okay.
So the way you get over that is just to not make the tubes that way, and sort of stress relieve them, and make sure you keep your stresses under control.
Okay.
Anyway, going back to our tubes, so the way it was done was that to make what are called zero clearance roll joints. So when you put the the tube inside the roll joint, essentially it's essentially a push fit, and so there's very little room to put a big stress in there, and if you don't drive the roller in too far, then you're fine. So the stresses came down by a great deal. Mm-hmm. So instead of having 700 or 500 megapascals, you got something like 100. So there was potentially a downside to that, because you get, instead of having circumferential stresses, you might get longitudinal stresses. But the nice thing about a longitudinal stress is it can't do much harm as far as the late hydride cracking is concerned.
Okay. Yeah. Yeah. So you were talking about these stresses in pressure tubes, but you also did a great deal of work on the stresses in the fuel sheaths themselves, and they were having problems. And I was wondering if you were, and the development of a lubricant.
A lubricant.
In fact, we've got some samples here of.
That's right.
Mm-hmm.
So this.
Feel free.
This is the kind of specimens that we made. So it's got three parts to it. In the center is soft aluminum, and outside of that is a ceramic, and outside of that is the
fuel sheath.
The fuel sheathing.
Yeah.
You can see it here. There's look at this part here. You can see there's the aluminum. There's the ceramic, and that's going to fit inside the little specimen of cladding. So what you do in the experiment is you put that right away down through there, and you squash that, and it squashes out and it breaks the ceramic, and the ceramic has cracks in it, and it's going to simulate, that's the simulation of the fuel. Mm. And so when you press it up sufficiently, that simulates increasing the power in the fuel, and it expands it. And that's what was causing the cracking in the fuel. So the cracking started with you put your fuel in the reactor at low power, and then when you move it in, when they're doing a bundle exchange, it goes to a high power, and that's when it was going snap, crackle, pop. Okay. And so it was expanding, and when it expanded, each of these cracks in the ceramic could essentially put the piece of fuel cladding into a tensile test.
Ah, it was actually stretching out the.
Stretching it out, yeah.
Okay. Okay.
So if I can give you that.
Yeah.
So this is an example of an experiment. So you can see here, if you don't do that and you just blow the thing up, it'll behave like that, and it'll neck down, and it'll burst over here. And you can burst it in the experiment. So here's the experiment. You're squashing down this, and right. You spread it out, and it forms a crack, and it'll concentrate in these places where there's a crack. Which is kind of as a good demonstration.
So if you put the fuel, if you put a bundle, we've got a slightly more modern bundle here.
Yep.
But if you put one of these directly into a high flux region, would it, or high power region, would it have the same problems with cracking, or was it only when you took it from low and then put it into a high?
It has been only from low to high, but it's you've got cracks there already, and I don't actually know the answer to your question, but you'd have to talk to a fuel person for that.
Yeah.
But so the things that are important are the number of cracks, the state of play of the cladding itself, and the lubrication. So these cracks, you can make them smaller. So you can make the You can make these crack strains. You can spread them out if you put lubricant in there.
Oh.
So that's where the graphite came from. So you put the graphite between the ceramic and the cladding, and it spreads the strain out.
Okay. Okay. So it's not actually lubricating the surface, is it?
Well, it's lubricating it in the sense that it's allowing these are spread out.
Okay.
The strain concentration is spread
Okay.
out.
Mm-hmm. Because at the time they were having a lot of fuel failures, weren't they?
Having some, not a lot. It was,
I thought it was in the order of sort of hundreds that they'd had in reactors. Different pins on different fuel bundles, and now it's a virtually unheard of.
It's very rare that it happens.
Yes.
Yeah. Mm-hmm.
Yeah. And of course, when you get a fuel sheath rupture, then you're actually starting to get water able to go into the fuel, and fission products can leak out into your coolant system.
It's all bad news. Yes.
Yeah.
Mm-hmm.
Yeah.
So it's not clear that what the other thing that happens when you do this expansion of the fuel, with moving it from low to high position of power, is you've got the chance of something like iodine, which is a fission product, or cesium, another fission product, getting into contact with the cladding and having stress corrosion cracking. So there's a big program on stress corrosion cracking to understand, what it takes and how can you stop it. And one of the ways to stop it is not to expand the fuel in this way. And so it may be that the graphite's got nothing to do with the actual strain thing as I'm proposing on here, but it's to do with stopping the stress corrosion cracking. Okay. And it doesn't matter because it works.
Yes.
Yeah, it was the way I did it.
Yes, I'd heard something along that line that it wasn't the mechanisms weren't fully understood, but it worked, and therefore continued to use it.
Well, that's right. And so when I wrote this paper about it, they talked about you using the siloxane and things, and it may be that it's helping prevent stress corrosion cracking. Nevertheless, the application of the results of the simulation has been most fortunate, even if done for the wrong reason.
So that's an honest, an honest approach. Yeah.
Yeah. Well, So the person that was doing a lot of that work was Clive Wood, and he did an enormous amount of work on that.
Ah, Clive Wood. He was a director of mine for a while out at Whiteshell.
Was he? Okay. So this wasn't an unknown kind of feature of nuclear fuel, and the Brits had done a lot of work on it, and the analysis that we used, the very simple part of the analysis was that the strain concentration depended on the coefficient of friction, and inversely proportional on the number of cracks and on the some property of the fuel cladding. Work hardening would be one of the properties that you'd look for. So you can do something about those, and that's what you're doing here by doing the changing the coefficient of friction.
Oh, okay. Okay. Amazing how much science and technology is involved in just tubes, whether they're pressure or in this case fuel sheath, that all this is happening, and there's so many mechanisms taking place. It's not a simple problem at all. It's occupied most of your career, right?
All of it.
Yes, all of it. Okay.
Well, because you're looking at zirconium, because it's an interesting beast in its own right, and looking at the application in a tube, and each of the tubes is different. Its application is different. Mm-hmm. So a calandria tube behaves in a completely different way from a pressure tube, which behaves in a completely different way from fuel cladding. And each of them has their own peculiar set of little problems to deal with.
So I can see it occupying your career. Yes.
Yeah.
Yeah.
And when you add in the wrinkles of irradiation damage, and of hydrogen, so I've spent an enormous amount of time looking at hydrogen effects.
And again, then is there any way to take away the problem of hydrogen getting in the first place?
Well, that's what the chemists and the corrosionists have been trying to do for years. And you can do some things. And so one of the things that we were looking at when we discovered that the fracture toughness was affected by irradiation, and only certain materials were affected by the irradiation. And you say to yourself, well, why was that? And it turns out that it was caused by residual iodine in the material. And you say, well, where does the iodine come from? Well, one of the fundamental processes for making zirconium is a process called the Kroll process. And within the Kroll process is a whole bunch of chlorine. Let me get this the right way. Yeah. Did I say iodine just now?
You meant chlorine.
I meant chlorine. I beg your
Yes.
pardon.
Oh.
Yes. Anyway. Yes, it's chlorine. So halogens play a big role in our business, don't they?
Mm-hmm.
So when we talk to the Russians, they have fluorine in theirs because they have the same kind of thing. So they get little fluorine particles in their materials. I haven't come across any bromine ones yet, but give them time. Anyway, so chlorine is part of the making the zirconium. And it's for a process called the Kroll process. And you'd think that the best way to get rid of it is just during the when you melt the material to make the material that you're going to make tubes out of and slabs and whatever else you're going to make. And so you have vacuum arc melting is what you use. And the vacuum arc melting it is quite good for getting rid of the chlorine. But what you find is if some of the tubes that were behaved really well, it turns out they'd been made out of almost completely recycled material. So if it had been recycled, it's been through the melting process twice. And so there's a good chance that you got rid of quite a bit of the chlorine. So we said to ourselves, what are we going to do about this? Let's melt it 4 times.
Okay.
And that's what we did. So you melt it 4 times, you get rid of all the chlorine, not all the chlorine, but you get rid of most of the chlorine. There's little residual amounts left. And when you irradiate that material, it's very tough.
Okay. But it also gets rid of hydrogen as well as the chlorine?
It also does that, and that's one of the other good things. At the time that we were doing this, we had a project to improve the pressure tubes. That was, and one of the ways to do it is to deal with, let's have a look at the chemistry of what the tube's made from. So we've got rid of the chlorine. By virtually melting 4 times, you get rid of a lot of the hydrogen. And there were sundry other things you want to get rid of. You want to get rid of phosphorus, you want to get rid of carbon, because they can be bad actors as well. So you can improve the fracture properties but by improving the chemistry of the material.
I see. I remember Dave Torgerson, who was my vice president at the time, our vice president of R&D, and he was very excited about quad melting. It was going to improve pressure tubes no end. This was in the 1990s, I seem to recall.
Yeah, that's right.
Yeah, very good. Okay.
And that's where that came from.
Yes. So, thinking of pressure tubes still, you were also involved in the group looking at NPD and
yes.
What should we do with NPD as it was now 25 years old or so?
That's right, yes. NPD had been a workhorse for the development. Can we make a pressure tube reactor work? Answer, yes. What can we use it for? Well, we can put some experimental fuel in there, and that's what was done. We used experiments of different pressure tube material. That was done. So we put, I'm saying we, the community realized,
Yes.
put zirconium 2.5 niobium in there and compare it with zircaloy. But the tubes originally were zircaloy 2. And zircaloy 2 is a magnificent material, except it picks up a lot of hydrogen. And one of the downsides of hydrogen is not only does it form hydrides, if you have enough of it in there, it'll be very brittle. And zircaloy could pick up a lot of hydrogen, which is what it did. And some of the tubes that were in NPD had gained a huge amount of hydrogen. And so one of the things that we used to do was to take specimens out, take tubes out of the reactor, chop them up into lengths and put a little flaw in them and blow them up to find out what kind of crack will grow in this tube. So you know the length of the crack, you know the pressure that it burst at, so you can get the plot of the length at which it cracks versus stress. And so that's what we did. So you do this at the operating temperatures, and what you really want is for this crack to be not very long. It turns out that when you have a huge amount of hydrogen there, and you get a crack that can propagate at the operating pressure, at the operating temperature. So one of the things about hydrogen is that you know what the solubility limit is, and by that you know when you have hydrides present. And so what you don't want is to have hydrides present at the operating temperature. And so in NPD, after 25 years, they picked up enough hydrogen that you'd have hydrides present at operating temperatures. So we said that's going to have to be looked at very carefully, which is what we did. And we looked at several. What you can do is you take a tube out and you have a look at it, and you make little fracture specimens, and you get a whole series of them, so you know how the fracture is behaving, and you find that at a certain temperature it becomes very brittle. So at a low temperature it's very brittle. At a medium temperature it's not brittle, and if that pressure is above the operating temperature, then you're okay. As soon as you get brittle behavior at the operating temperature, then you say to yourself, that is not very good. Let's not carry on using this reactor because of this. So you couldn't guarantee a leak before break, and you couldn't guarantee leak before break in NPD. I always get that wrong. Because they didn't have an annulus gas. It was open to the atmosphere.
I didn't know that.
And so, getting a puddle on the water of the reactor, on the reactor floor, didn't seem to be a good idea. Whereas when you have an annulus gas, you can pick it up in grams of water, and so it's done by dew point.
Okay.
And change of dew point. So you could measure the leakage very, very, very easily. So that was the story on NPD. So we told the powers that be that we don't think these tubes are very good. I think we should change them. And people said, well, we're not going to change in that reactor. It's not worth it. It's a toy reactor. So all that material was available for experiment, and it had its day. And so that's the story of NPD.
Yes, I recall finding a brochure on NPD. I have in one of my collections, and it said that when it was built, they were thinking it was going to have a 10-year life, and yet it ended up having a 25-year life.
That's right, yes.
Quite remarkable. At the time, they didn't, of course, it was the first power reactor in Canada and the first of the can-do type design, so they didn't really know how long it could last. And so, nonetheless, it was 2.5 times its intended life. It was a quite remarkable reactor.
Oh, it was remarkable for all the other features that, the experience it gave people. And I guess the Ontario Hydro people, I guess, would get experience on being around a nuclear reactor by being at NPD.
Yes, with the training school there
Yeah.
as well.
Yeah.
Oh, that's interesting. I didn't know that was the problem. So yeah, I noted earlier you were talking about Kroll having developed the method of, I guess, for creating the zirconium feedstock.
That's right. Yeah.
So and of course the Kroll metal is named after him.
And it's made of zirconium.
And it is made of zirconium. Okay, and you are one of the recipients of this.
I have, yeah. I'm not quite sure who made the case. I don't know how they did it, but anyway.
It's sort of like the Nobel Prize of
zirconium.
Of zirconium, yes. Yes, and we even have one in our collection here, a Kroll medal. I forget whose it was. So that's quite remarkable.
So nowadays what they do is that the ASTM runs the Kroll medal thing, and they invite you to write a paper on it. So you make a presentation and then write a paper on it. So that was my paper for the Kroll thing. So I wrote it on the simulation of behavior of zirconium alloy components in nuclear reactors. So I did it on the cladding, so I gave the can-do story. I did it on pressure tubes, giving the leak before break story, and on calandria tubes, because we made some improvements. Well, it would be nice to think that we made some improvements to calandria tubes. So, of course, you can do several things with calandria tubes. You can make them seamless instead of welding just a sheet of zirconium and putting a weld down it. Just make them with no weld. So make them seamless. So the neat thing that you can do when it's seamless is you can do things to the surfaces, and that helps with the heat transfer. And so if it helps with the heat transfer, then it helps you with mitigating some accidents. And so that's one of the things that we had a shot at doing.
Oh yes, yeah. That was the was that the shot peening or
shot peening?
Yes.
And the other thing you can do when it's seamless is as you're making the tube, you can actually put little ridges on them. So instead of being smooth, the pressure tube, when it expands in an accident, touches it just at points, and so you get bubbles forming there, and so you get good heat transfer.
Yes, without going into film boiling.
That's right.
That's a field I began my career at ACL was taking pressure tubes and ballooning them for in accident conditions. It was very interesting work. Sometimes they blew up. Sometimes they didn't.
That's right. So we did this with these little ridges. Excuse me, and with shot peening the surface, and you can get a very effective way of not getting film boiling. Or at least to higher temperatures of the water.
Yes, that's correct.
So it makes it seamless. It makes it, So the shot peening was actually used in Xinshan.
Oh yes, okay.
The idea being that their cooling water may not be as cool as you'd like it to be.
Right.
And so it gives you a margin on your accident.
Yes, and also there was blackened pressure calandria tubes, wasn't there as well?
That's right. That helps with the
radiation.
With the radiation, yeah.
Yes. Oh, this is interesting to see where your input into what the things that I knew and experimented with. So, have you got any comments on recently with reactors at Bruce and Darlington? They've had pressure tube a couple of problems with Bruce pressure tubes, that they were concerned with the high amount of hydrogen in them.
That's one of the things, yes, and not really. I'm not completely familiar with it. Remember, I'm not really a working person anymore. So, but I did listen into the commentary at the IE's, not the IEA, the CD, what do they call it?
CNSC?
The CNSC, yeah, where they were talking about it, yes. Yeah. And that again is at the roll joint. And the interesting thing about the roll joint is you seem to pick up a lot of hydrogen there, and it's not really clear why. You shouldn't do it. One of the thoughts that I work with Glenn McRae at Carleton, and one of the thoughts we had was that it was the hydrogen was coming from the end fitting itself. It was gathering the hydrogen from the steel. So it wasn't a corrosion issue at all. It was just a gathering process.
Oh, okay. I hadn't heard that. Okay, that's.
Well.
So in other words, if you improved your end fittings, getting rid of hydrogen in them in the first place, then you could reduce this problem.
That's right. So that was one of the suggestions we made, was to, with your end fitting steel, make sure, if there's 1 part per million in there, then have get it down to 100th of a part per million, and then you won't have a problem. It's a steel. It might be a steel problem rather than a zirconium problem. So we've done some, itsy bitsy, teeny weeny laboratory experiments where what the student did this on his own hook. He took a piece of zirconium tubing, and he had a piece of steel bar, and he sort of crunched them together, and he put them in a furnace for a few days, and took them out and measured the hydrogen in it, and he picked up 40 parts per million of hydrogen out of the steel. And you say, how on earth did you do that? Well, that's because there's a lot of steel and a little bit of zirconium, and so he got to get the hydrogen out of the steel.
Wow. Okay.
So you've got to be careful with all these things. But when you join a piece of metal to another piece of metal, strange things can happen. So you've got to be always.
When they're dissimilar metals, yeah.
That's right. Yes.
Yeah.
And even when they're not too dissimilar, you can do that as well.
Well, that's an interesting, because it's posed a big problem for Bruce in particular.
Yes, I understand that, but I'm not quite sure whether it's every tube or just 1 or 2 that are affected.
I don't know. Yeah.
So the other thing that I was involved with Bruce, and that was just this last year, was they were concerned about the tertiary creep of the task group 3 tubes, which are a different way of making the tube, and the 3 of these tubes in the reactor, and they'd measured the diameter of these things, and they were quite large. But what they'd done is they measured these at intervals, and so there's very good information on that. And so if you analyze the shape of the deformation, you can show that it's actually still in primary creep after 250,000 hours or whatever it is, a great long time. So I made the plea that it was still in primary creep. It's nowhere near tertiary creep. So you're in good shape.
Oh, okay, yes.
And so Malcolm Griffiths and I were working on this, and he came at it from a sort of a microstructural in-reactor creep point of view, and I came at it from the point of view that I've just talked about on what I did when I first came to Chalk River. So it was useful after all.
I see. I see. Your first work was important. Okay. So, following retirement, you've been involved with writing a book.
Writing a book, yes. So the IAEA said that would support a book, and they didn't really know what they were doing. They'd already put a book out on zirconium in about 1976 or so, which was very useful. But it was written by one person, and it was quite extensive. But a lot of water's gone under the bridge since then, and there's been a lot of information. And so I suggested to him that we write an update of this. And you say to yourself, well, that was a bit of a mistake, wasn't it? Or it turns out, yes, it was. Because I gave them an outline of what we should do, and then said, well, we should really get more people to do this so we can get somebody who can focus on different parts of it. So that's what we did. And I wrote an outline of how it should be divided, and I got some co-authors and people to help. And so we started to write, and they said, yeah, we'll give you a little bit of money for this. And so it got written. And but it took a long time. It took a long time because I'm not being rude, but there were some people where English wasn't their first language, so you had to do something with the language, and the IAEA, unbeknownst to me, had got into trouble by, in some of their reports, had taking diagrams out of the literature without giving the proper credit and sometimes proper crinklies to pay for the use of these diagrams. And we had to go through the whole thing to find out about what to do with these diagrams. So generous ACL said, oh no, you can use our diagrams, so that was fine. So there was diagrams from Chalk River, but things from Elsevier and ASTM and so on had to be paid for. So I had to go around cap in hand with all this and identify all the diagrams. It was a pain.
But it is work that is now finished for you.
It is finished, and I'm surprised I haven't received copies of it. The main problem, as far as I'm concerned, is that it's about 5 years out of date.
So
maybe in some parts more than 5 years, and maybe in other parts it's actually was spot on at the very beginning. So, so I'm disappointed in as much as that. Say the consequences of Fukushima have not been included, and since that happened, there's been a whole bunch of lots of good work done on trying to make accident tolerant fuel.
Yes,
and that there's not a dicky bird in there about accident tolerant fuel.
It will have to be published then, and second edition.
Yeah, okay. So you're volunteering to do the second. So it is disappointing. So I had. Brian Cox was one of the authors, and there was a fellow at Hua Chang who was helpful. Yeah, I had Brian Cox, but unfortunately he's not with us anymore, so he can't do anything about it to help it. The people at Hua Chang were quite generous, and they helped. There's a French gentleman called Lamagnon, who was the famous metallurgist. So he wrote a section. A lady in Russia, a lady called Nikulina, unfortunately she's just died, so she's not going to see a finished copy. So it's this kind of thing that's so upsetting, that the people who were involved with setting it up are no longer with us. And I'm not a spring chicken, so.
So, to sort of wrap things up, are there things that sort of, now that you've retired, things that you would have liked perhaps to have changed or wish that the company had done instead over the years?
Well, I had, as you could gather, I had a good time.
Mm-hmm.
It was a pretty wonderful place to work because the work was interesting. The people that we were working for were also interested and they supported you, and you even went to conferences and you got stuff published and what more do you want?
Mm-hmm.
Yeah, and they paid me.
Yes.
We got to look at pretty microstructures and that's a joy in itself, isn't it? The neat thing, you asked about living here, and it was a great place to live and work because you could run home.
Oh, yes.
And I used to do that. And we got into running marathons. What I sometimes would run both ways. And so the group of us did these. And one of those people was a metallurgist. And we worked together on zirconium chromium alloys. And we decided that we'll try to understand about running. So we wrote a paper on it.
Oh.
And we wrote it and we sent it off to Nature. And they published it.
Oh, very good.
But that's what it looks like.
Analysis of running and the prediction of ultimate performance. Complete with mathematical equations.
One mathematical equation, yes.
What year was this?
1970.
1970.
Yeah. Now, the really downside about it is that it doesn't use SI units. I should really update it and put it into SI units and things. But the neat thing about it is that this works with speed skating. You can make the formulation in here work with speed skating. Because in speed skating they have a competition in the year where they do a 500, a 1500, a 5000 and a 10,000, or a range of distances. And you can do this analysis that we did on running, on speed skating. And it works really well.
Oh.
Except for one athlete who's so good, he destroys the whole thing. But for a lot of them, it works really well.
So
what it is it's just the rate at which you run as the distance that you're running, and the slope of this line is the thing that we're measuring.
Okay.
And you can use that and put it against some very famous runners and the world record holders and things, and you can plot their range of expertise, as it were, and where they intersect. When these guys have a good race, between each other, you can't predict who's going to win.
And Nature publishes. Very
and
good.
Nature published it. Wasn't that nice of them?
Yes.
Anyway, you can have that.
Very good. Well, thank you. That's another interesting artifact for us to keep in our museum here. Was this running on the old Balmer Bay Road?
Yeah. We just used to run home. Yeah.
Yes. So I think that comes to the end of the questions I have, and it's been really very interesting. Certainly, personally, since I know some of this history of pressure tubes, have worked with them, and calandria tubes, and so it's been a real delight talking to you today. And thank you so much for your time with us.
You're more than welcome.